Good day, everyone. I'm Arvin Enriquez, your subject teacher for Probability and Statistics. With this video lesson, we're going to discuss the following topics: your random sampling, parameter and statistics, and sampling distribution of statistics. Our lesson objectives: at the end of this lesson, you are expected to illustrate random sampling, distinguish between parameter and statistics, and identify sampling distribution of statistics or your sample mean. Let's deal now with the formal definition of a sampling. Your sampling means selecting a particular group or sample to represent the entire population. So you need to take note of that. When we say sampling, it's about selecting a particular group or sample to represent the entire population. In research, it is a process used in the statistical analysis in which a predetermined number of observations or sample are taken from a larger population. As you can see in your figure A and B, so there is a population here. So under your population, there is what we call sample. Same thing with your population here in your figure B. Under your population, there is a sample under to your population. So in research, we don't need to subject your entire population in your research. What we need to do is to get a sample from that population, and this sample will be subjected to your research that will represent your entire population. Again, in your research, we don't need to subject your entire population. What we need to do is to get a sample from that population, and this sample will be subjected to your research to represent the entire population. Now, let's deal with the formal definition of your population and your sample. A population refers to the entire group that is under study or investigation. Or we can say that this population is the entire group that you want to draw conclusions about. Now, dealing with your sample, a sample is a subset taken from a population. So you need to take note of that. Your sample is a subset taken from a population, either by random or non-random sampling techniques. A sample is a representation of the population where one hopes to. Or we can say that this sample is the specific group that you will collect data from. The size of the sample is always less than the total size of the population. It should be less than, because this sample is under to your population. That's why your sample or the number or the size of your sample should be less than to the total number of your population. In research, no, a population doesn't always refer to people. So you need to take note of that. A population does not always refer to people. It can mean a group containing elements of anything you want to study, such as, for example, objects, events, organizations, countries, species, organisms, and etc. As a researcher, for us researchers, it is important to carefully or we can define your target population according to the purpose and practicalities of your project. So you need to look for, or we need to define your target population. And it will be dependent to the purpose and practicalities of your project. So you need to take note of that. If the population is very large, demographically mixed, and geographically dispersed, it might be difficult to gain access to a representative sample. So you need to assess your population if that is large, very large. So if that is demographically mixed and geographically dispersed, you need to rethink if that population is the right population to be subjected in your research. Let's deal now with your sampling techniques. So it can be random sampling and your non-random sampling. So under your random sampling, so it can be simple random sampling, systematic sampling, stratified sampling, cluster sampling, and multi-stage sampling. So under your non-random sampling, so it can be purposive sampling. Next is that incidental or accidental sampling. And your last is your quota sampling. Let's deal now with the types or type of random sampling technique. Your random sampling technique gives every member of the population equal chance to be selected as part of the study. Here is the 5 sampling schemes of this type. First is your simple random sampling. Is made when all the members of the population are given a chance to be selected. So what we need to take note for this simple random sampling is that all members of the population are given a chance to be selected. Selection is done by draw, lot, or the use of the table of random numbers. So each members under your population are given a chance or an equal opportunity to be selected and to be subjected in a research. So in a simple random sample, every members of the population has an equal chance of being selected. Then your sampling frame should include the whole population. To conduct this type of sampling, you can use tools like random number generators or other techniques that are based entirely on chance. So for example, so I'm going to give you an example. You want to select a simple random sample of 100 employees of company X. You assign a number to every employee in the company database from 1 to, for example, from 1 to 1000, and use a random number generator to select 100 numbers. So each number that we can get from the random number generator will be subjected to your research. This will be your sample now. That's why dealing with this simple random sample or simple random sampling technique, no? all the members, or every member, should I say, of the population has an equal chance of being selected. So there is an equal opportunity for them to be selected and to be subjected in your research. Our next sampling technique is that your systematic sampling. So when we say systematic sampling, is choosing the end name in a population as the sample. It entails using a list of the population and deciding how the end name is chosen. For example, the population of students in one school is listed alphabetically and numbered consecutively. From the list, the sample to be taken is the name that falls every end in the list until the desired number of sample is completed. So with the population of 500 and 250 as the desired sample, the individual sample may be the name that falls in every count of 2 or all those that are in the odd number or the even number. For example, if the number if the total population is 5,000 and the desired sample is 100, then your sampling interval will be equal to the total population over your desired sample. So therefore, that will be equal to 50. Now, with your sampling interval, you're going to use this sampling interval as your basis. So in getting your sample. First, get the number 50 as the first sample, and every 50th person in the list for 100, 150, 250, 300, 350, 400, 450, 500, and etc. until the 100 respondents are completed. Meaning to say, in choosing your uh, sample, it will be dependent on the value of your sampling interval. Now, with your systematic sampling, it is somehow similar to simple random sampling, but it is usually slightly easier to conduct because there is a sampling interval involved. So every member of the population is listed with a number, but instead of randomly generating numbers, individuals are chosen at regular intervals. That's why it, it is slightly easier to conduct because of your sampling interval. So let's give another example of this one. So for example, all employees of the company are listed in alphabetical order. From the first 10 numbers, you randomly select a starting point. For example, number 6. From number 6 onwards, every 10th person on the list is selected. So that will be 6, 16, 26, 36, and so on. And you end up with a sample of 100 people. So our next sampling technique is that your stratified random sampling is dividing the population into strata and drawing the sample at random from each division. So for example, so the population to be sampled are the elementary school teachers in one district. These are stratified by their ranks as teacher 1, 2, and 3. Samples of equal number are drawn from each rank. This method is used when there is a ready list of the population whose members are categorized as students, farmers, fishermen. The steps to follow are, so we need to follow the following steps. So get the list of the total population. Then next, decide on the sampling size or the actual percentage of the population to be considered as your sample. That's why we don't need to subject your entire population. So what we need to do is to get a sample from that population to be subjected in your research. So here, you need to decide on the sampling size. Next to that is that we need to get an equal proportion of samples from each group. So for example, so 500 pupils, so we multiply these 500 pupils by 0.20, so that will be equal to 20% here, or simply equal to your 100. So your 200 teachers will be multiplied same thing with your 20% here, or that will be equal to 40. Same thing with your parents, that will be 150 parents multiplied by 20%, or simply equal to 30. So if we get the total sum of these three resulting values, that will be equal to 170. So get the 170 respondents by simply random or systematic sampling. In your stratified sampling, it involves, please do take note of this, it involves dividing the population into subpopulation that may differ in important ways. So it allows you draw more precise conclusion by ensuring that every subgroup is properly represented in the sample. Now, to use this sampling method, you divide the population into subgroups called strata. So please do take note of this. So the another term for that population into subgroups. So your subgroups, another term for that is your strata. Based on the relevant characteristics. For example, gender, age, range, income bracket, and job role, and etc. For example, so based on the overall proportions of the population, you calculate how many people should be sampled from each subgroup. Then you use random or systematic sampling to select a sample from each subgroup. So I want you to give another example of this one. So for example, let's deal now with the company again. So the company has 800 female employees, for example, and 200 male employees. So a total of 1,000 employees. You want to ensure that the sample reflects the gender balance of the company. So you sort the population into two strata based on gender. So that will be your male and female. Then you use random sampling on each group, selecting 80 women and 20 men, which gives you a representative sample of 100 people. So that's how we deal with your stratified random sampling. The next is your cluster sampling. It's a design that uses a group as sample rather than an individual. So for example, the population may be the parents in one school district. The parents may be grouped by barangay within the district or by those in the east, west, north, and south of the district. From these groupings, the same cluster is chosen randomly or systematically. This differs from stratified sampling that includes all the strata in the sampling process. So what is important about your cluster sampling is that it uses a group as sample rather than an individual. So dealing with your cluster sampling, it involves dividing the population into subgroups but each subgroup should have similar characteristics to the whole sample. Instead of sampling individuals from each subgroup, you randomly select entire subgroups. So you need to take note of that. If it is practically possible, you might include every individual from each sampled cluster. If the clusters themselves are large, for example, you can also sample individuals from within each cluster using one of the techniques, or for example, stratified sampling. So this method is good for dealing with large and dispersed population. So we use this cluster sampling techniques in dealing with large and dispersed populations. But there is more risk of error in the sample, as there could be substantial differences between clusters. So if there is a difference, no, or differences between clusters, so there is more risk of error in the sample. It's difficult to guarantee that the sampled clusters are really representative of the whole populations because of the differences that exist between clusters. So for example, so let's give an example of this cluster sampling. So let's deal now again with your company. So the company has offices in 10 cities across the country, all with roughly for example, roughly the same number of employees in similar roles. So you don't have the capacity to travel to every office to collect your data. So you use random sampling to select 3 offices. So these are your clusters now. So our next sampling technique is that your multi-stage sampling. So this multi-stage sampling is done by stages. From its name, multi-stage sampling. 2, 3, 4, as the case may be depending on the number of stages sampling is made. Here, the population is grouped by hierarchy from which sampling is done in each stage. For example, the population to be studied consists of the personnel in the public elementary schools in the country. So samples have to be taken from the national, regional, provincial, district, and school levels. This will be your example. So first level, so 3 municipalities per province. Second level, 2 districts per municipality. Third level is that 4 barangays per districts. Then fourth level is 100 respondents per barangay. Use any of the sampling techniques given a while ago in arriving at the desired sample number. Here in your multi-stage sampling, or we can define your multi-stage sampling as a sampling method that divides the population. That's why we need to divide the population into groups or clusters for conducting research. It is complex from a clustered sampling. No? It is more complex uh, form of a cluster sampling, sometimes also known as the multi-stage cluster sampling. So another term for your multi-stage sampling is your multi-stage cluster sampling. So please do take note of that. During the sampling method of this sampling technique, significant clusters of the selected people are split into subgroups at various stages to make it simpler for primary data collection. Now, the question is that What are the steps to conduct multi-stage sampling? So there are four multi-stage steps to conduct, no? So your step one is that choose a sampling frame. So we need to choose a sampling frame considering the population of interest. The researcher allocates a number to every group and selects a small sample of relevant separate groups. Then going to your step number two, so select a sampling frame of relevant separate subgroups. So we're going to do this in a form of or from related different discrete groups selected in the previous stage. In your step three, repeat the second step if necessary. So if it is necessary, so we need to repeat your step number two. Then step number four, using some variation of probability sampling, we need to choose members of the sample group from the subgroups. So next question is that what are the application of multi-stage sampling? So we can apply this multi-stage sampling or multi-stage sampling is applied mainly to these areas. So first is that we can apply to a multi-stage design where the population is too vast and researching every individual is impossible. So that will be your first application. Your second is that to gather student perceptions from students belonging to various colleges studying different courses and located throughout, for example, throughout the country. Then third, to survey employees of a multinational company belonging to multiple locations in multiple countries. Then last, it can be government bureaus use this method all the time to draw inferences, from the population. Then this multi-phase sampling reduces the time taken to research an area. It also keeps a tab on the cost of the research. The information collected from the samples is used to draw inferences from the population as a whole. So in this slide, we're dealing with your random sampling technique. So a random sampling technique is the opposite of probability. So this will be your non-probability sampling technique. So here, the researcher's judgment determines the choice of the sample. So there are three kinds commonly used non-random sampling technique. So your first one is your purposive sampling. In this design, the samples are chosen based on the judgment of the researcher, who determines an individual as sample for possessing special characteristics of some sort. Or another term for this for positive sampling is the your judgmental. It can be selective or subjective sampling. So it's a form of non-probability sampling in which researchers rely on their own judgment, when choosing members of the population to participate in their study. So this sampling method requires us researchers, to have prior knowledge about the purpose of our studies, so that we can properly choose and approach eligible participants. So we need to know what is the purpose of our studies. So we researchers use purposive sampling when we want to access a particular subset of people, as all participants of a study are selected because they fit a particular uh, profile. Next is your incidental or accidental sampling. As the term implies, this design is used to take samples who may be the most available or the nearest at the time of data gathering. So your accidental sampling, also known as a grab or opportunity sampling because of it's accidentally, is a form of non-probability sampling, or it's another form of non-probability sampling that involves taking a population sample that is close at hand rather than carefully determined and obtained. So for instance, a person who is obtaining opinions for a political poll at a shopping mall by randomly selecting passers-by is using a form of accidental sampling. No, accidental samples are not as experimental. So you need to take note of this. It's a different thing when you say experimental. That's why accidental samples are not as experimental. Sound as using random sampling and random assignment. Next, so for your quota sampling, a design popular for opinion research, this sampling is made by looking for individuals that possess the required characteristics or prescribed criteria of the research. So in your quota sampling, no, it's another technique under your non-probability sampling in which researchers create a sample involving individuals that represent a population. So we researchers choose these individuals according to specific traits or qualities. So we decide and create quotas so that the market research samples can be useful in collecting data. So these samples can be generalized to the entire population. So the final subset will be decided only according to the interviews or researchers' knowledge of the population. No? For example, a cigarette company wants to find out what each group prefers, what brand of cigarettes in a particular city. He or she applies quotas on the age groups. For example, 21 to 30, 31 to 40, 41 to 50, and 51 plus. So from this information, the we researcher gauges the smoking trend among the population of the city. So in this slide, we're going to determine the sample size. So for example, for a population of more than 100, sampling is a mass. So following is a formula for scientific sampling, illustrations and examples, your Calmorin and Calmorin 1995. So here is the formal formula in determining the sample size. Your SS will be your sample size, your N is the total number of population, your B is the standard value, which is 2.5 of 1% level of probability with 0.99 reliability. So your SE here is your sampling error, and your P is the largest possible proportion, which is equals 0.5. Now, let's talk about your sampling error. So when we say sampling error is the difference between a population parameter and a sample statistic. No. For example, in your study, the sampling error is the difference between the mean political attitude rating of your sample and the true mean political attitude rating of all undergraduate student for example, in the Philippines. So your sampling errors happen when you use, a randomly selected sample. This is because random samples are not identical to the population in terms of numerical measures like means and standard deviations. Because your population mean is not equal to your sample mean, then your population standard deviation is not equal to your sample standard deviation. That's why there is an existing sampling errors. So that's it. So to illustrate the formula, these steps have to follow. First step, so determine the total population, so that will be your n, assumed to be static. For number 2 or step number 2, so get the value of b, which is 2.5, your s is 0.01, and your p is 0.5. So compute the sample size using the formula. So for example, and the application of this formula, the total population is 500, has a standard value of 2.58 at 1% level of probability and 99% reliability. The sampling error is 1% or 0.01, and the proportion of a target population is 50% or 0.5. Now, the sample size is computed as follows. First, you need to identify the given values. So your N or your total population is equal to 500. Your B or your standard value is equal to 2.58. Your sampling errors or error is equal to 0.01. And the proportion of the target population is equal to 0.5. Now, with our solution, substituting the given values, so we substitute your 500 multiplied by 2.58 here, plus your 0.01 square multiplied by 1 minus 0.5 all over your 500. That will be your total population multiplied by 0.01 plus your 2.58 multiplied by 2 multiplied by 0.5 multiplied by 1 minus 0.50. So as we simplify your resulting value from this numerator and denominator, so that will be 1 to 90 plus 0.0005 all over 6.6641. So as you can see, using your calculator, we can simplify this one by, so your SS or your sample size now is 193.57 or 194. So your sample size should be a whole number and not in terms of decimal, because there is no such thing as a, for example, a person which is equal to 0.57. So it should be a whole number and not in a decimal form. That's why 193.57 is approximately equal to 194. Therefore, this sample size of 194 represents the 500 subjects of study. So another formula in finding the sample size is your Islevin's formula. So your n is equal to n, that will be the population size, all over your 1 plus your n, that will be your population size again, and then your e is the margin of error square. So n here is your sample size. Now the question is that when Slovin's formula is used. So when we can use this Slovin's formula? So first, your Slovin's formula is used to calculate an appropriate sample size for a population. So when we can use it? So if you have no idea about the population's behavior, use Slovin's formula. So you need to take note of this. Again, if you have no idea about a population's behavior, use Slovin's formula to find the sample size. No, the formula, or sometimes written as Slovin's formula, was formulated by Slovin in 1960. So the error tolerance E, or the margin of error here in your formula, no, can be given to you if you are a researcher. You might want to figure out your own error tolerance. Just subtract your confidence level from 1. For example, if you wanted to be 98% confident that your data was going to be reflective of the entire population, then 1 minus 0.98 is equal to 0.02. Or simply your margin of error is equal to 0.02. So that will be the value of your E. No, the value we can compute for the value of your E, and it will be dependent on uh, the number or the percent or the confidence level that we wanted as a researcher. So whatever value that we're going to put as a value of your confidence interval, that will affect, no, the value of your margin of error. Here is the example how we apply the Slovin's formula. So your example, a researcher wants to study the academic performance in mathematics of students in a certain school. The school has a population of 12,000 students. If the researcher allows a margin of error of 5%, how many students must be included in his sample? So there is a given value of 12,000 here and a 5% error here. Now, we simply substitute the given values for us to find the value for sample size. So 1, 2 over 1 plus 1, 2 multiplied by 0.05. That will be your margin of error square. Then we simplify, no? By simply simplifying, then going to this one, no? Or there's a typo error here. There is no n here. So you need to erase this n. Then your n now is equal to 1, 2 over 1 plus 30. Then your n is equal to 1,200 over 31, and the resulting value now is 387.096. So thus the researcher must take 387 students as his sample. Sir, why we don't consider your 0.96 here? Because it's less than zero point 0.5. So if this is greater than zero point 0.5 or zero point 0.5, it should be 388. But again, 0.096 is less than zero point 0.5. That's why we only consider this sample size that it will be equal to 3.87 students. So let's deal now with your parameter and statistics. So a statistics is a number which describe a sample. It can be directly computed and observed. So an example of statistic is the sample mean, which serves as an estimator for the population mean because it will represent your population mean partially, no, but not equal to your population mean. So examples of statistics are sample mean, your sample standard deviation, and your sample median. So dealing with your statistics now. So when we say again with your statistics, it is the number that describes the sample. So it can be calculated and observed directly from our formal definition. So the statistics is a characteristics of a population or sample group. You will get the sample statistic when you collect the sample and calculate the standard deviation and the mean. So you need to get the value of your standard deviation and your mean. So you can use sample statistic to draw certain conclusions about the entire population. So for example, 50% of people living in the Philippines agree with the latest healthcare proposal. Researchers can ask hundreds of millions of people if they agree. So they take samples or part of the population and calculate the rest. That's why it is important for us to know how to get a sample from a population. And this sample will represent the entire population in our study. And next example. So researcher interviewed the 70% of COVID-19 survivors. So that will be your statistic. Now, dealing with your parameter, so when we say parameter is a descriptive measure of a population, while a statistic can be directly computed and observed. So the value of if a parameter can be approximated and is not necessarily equal to the statistic of a sample. So best example of this is your population mean, your population standard deviation, and your population median. So when say parameter again, with your formal definition, it is a descriptive population measure. So it is a measure of the characteristics of the entire population. For example, a mass of all the units under the consideration that share common characteristics. So dealing with your parameter, when we say it's a characteristics of the entire population, a mass of all the units under the consideration that share common characteristics based on all the elements within the population. So example, all people living in one city, all male teenagers worldwide, all elements in a shopping cart, and all students in a classroom. Next example is that the researcher interviewed all the students of the school for their favorite apparel brand. So let's deal now with your sampling distribution of sample means. So a sampling distribution of sample means is a frequency distribution using the means computed from all possible random samples of a specific taken from a populations. So this sampling distribution of sample means, for example, how we compute your probability that will be mapped in each random variable that we have in your probability distribution of a random variable. It's the same process on how we compute your probability in your sampling distribution of a sample means. It is the same scenario, no? The only difference is that we're dealing with the means or the sample means that is being involved in this kind of sampling distribution. Unlike before, we're dealing with a random variable. Now we're dealing with a sample means. So what will be the probability that will be mapped in each sample means reflected on our table? So that will be the case now. Now, the probability distribution of the sample means is also called the sampling distribution of the sample means. So it's another term for your sampling distribution of the sample means is your probability distribution of the sample means. So this will be your another term for your sampling distribution of the sample. Steps in constructing the sampling distribution of the means. Determine the number of possible samples that can be drawn from the population using the formula. So we apply here the concept of your combination. So your n is your size of the population and your small n is the size of the sample it involves. No. For step number 2, list all the possible samples and compute the mean of each sample. Then for number 3, construct a frequency distribution of the sample means obtained in step number 2. So you need to deal with the sample mean and you need to construct for a frequency distribution of the sample means based on the values that we can get from your step number 2. So for example, so a population consists of the numbers 2, 4, 9, 10, and 5. So we need to list all the possible samples of size 3 from this population using your 2, 4, 5, 2, 4, 9, 10, and 5. So compute the mean of each sample, then prefer a sampling distribution of the sample means. So as part of our solution, the possible samples of size 3 from 2, 4, 9, 10, and 5 are the following. So from 2, 4, 5, 9, 2, 4, 9, 10, and 5, what are the possible combinations that we can get dealing with size 3? So this will be your 2, 4, 9, 2, 4, 10, 2, 4, 5, 2, 9, 10, 2, 9, 5, 2, 10, 5, 4, 9, 10, 4, 9, 5, 4, 10, 5, and 9, 10, 5. So these are the possible samples that we can get, or the possible combinations that we can get from your 2, 4, 9, 10, and 5 with a size 3 here. So as the continuation of our solution, we're asked to find the mean of each sample are as follows. So in your first column, these are the possible combinations that we can get from the numbers being involved with the size 3. So how we can get the mean of this one? So we just simply take we just simply get the average of these three numbers. So that will be 2 plus 4, that will be 6 plus 9, 15. So if we divide this 15 by 3, so that will be 5. So same scenario up to the last value or last possible combination that we can get from the numbers involved. So if we add 9 plus 10 plus 5, so that will be 15 plus 9 or 24. So if we divide this 24 by 3, so that will be equal to 8. So same process to each value, no, uh, of your sample or possible combinations that we can get from the numbers involved with the size 3. So how we can get the mean is that we need to get the average of these three numbers. So we just simply get the total of these three numbers, then we divide it by 3 to get the value of your mean that will be mapped in each possible uh, combinations that we can get from the numbers involved. So as a part of the continuation of our solution, we're asked to construct the sampling distribution of the sample means. In your first column, this will be uh, your sample mean from our computed value in the previous slide. Now, what will be the frequency that we can assign from each sample mean from our first column? That will be your second column. Now, whatever the values from your second column, that will be your values for your frequency. Your frequency will represent how many times these sample mean reflect as a value of your X bar in your previous slide. So since 3.67 uh, reflected on our table only once, no, then the value of your frequency that we can assign from this 3.67 is equal to 1. So same scenario with your 8 up to the last value. Since 3.67 and up to 8 as your value of your sample mean reflected only uh, one time, no, in your previous table, then the frequency that we can assign from each value of your sample mean is equal to 1. Now, if we get the total of this one, it should be equal to 10. That will be your sample size now. So the total or sum of these frequencies under your second column must be equal to 10 or your total sample size. Now, how can we compute for the probability? So we define your probability as your desired outcomes over your total possible outcomes. Since your total possible outcomes is 10, that will be your total number of sample size, no? Then 1 is how many times does your 3.7 reflect as a value of your sample mean. That will be your numerator here, or that will be your frequency that will be mapped in each sample size here. So therefore, that will be equal to 1 over 10. Your 10 here as your denominator is your total sample size. Same scenario. Since your frequency in your 5.33 is 2, then your numerator in your probability that will be mapped in your 5.33 is equal to 2. Now, how can we check if your table is a sampling distribution table? Again, same concept with the probability distribution table. So we need to get the total or sum of these probabilities under your third column. If the total or sum of these probabilities under this third column is equal to 1, then your table is a sampling distribution table. So in your activity number 1, you need to identify the type of sampling method that we can use on the following scenario. So write your answer on a separate sheet of paper. Decide whether the statement describes a parameter or statistics. That will be your activity number 2. So write your answer on a separate sheet of paper. So you need to write, no? Or you need to decide whether the statement describes a parameter or statistics. So again, dealing with your statistics, you're dealing with the sample, and parameter, you're dealing with a population. So for activity number 3, a group of students got the following scores in a test. That will be 6, 9, 12, 15, and 18, and 21. Consider samples of size 3 that can be drawn from this population. So you're going to look for the possible combinations that we can get from your 6, 9, 12, 15, 18, and 21. Then list all the possible samples and the corresponding mean. Then construct the sampling distribution of the sample means. So thanks for watching. If you want to like, comment, share, and subscribe, please do so.